So now we're basically looking at what is going to be the fate of a star of at least 8 solar masses. Some people say it needs 15. Some people say it needs only 3 solar masses, depends on the model. And there's of course nuclear physics. Then there's this magnetohydrodynamics that describes the flow of a plasma, then how much is the star rotating, and stuff this is well beyond my capabilities. So I just deliver these nuclear physics inputs. And hopefully you have seen the video. Next couple of 100,000 years, maybe tomorrow, maybe 200,000 years, we're going to sit in the front row when Betelgeuse explodes. By the way, Betelgeuse, these names often, Aldebaran, Deneb, many names of stars, most of them are of Arab origin. This has simply the reason. While we were busy fighting each other and burning witches, the Arabs cultivated knowledge. And astronomy was one thing. And astronomy, well, there were the centers of exchange. Less so the Holy Land, there we were busy fighting each other. Sicily, for example, was a center where Christian culture as well as Muslim culture met, or Spain, of course, with the Moors coming over and giving Spain the Alhambra. Beautiful buildings, beautiful architecture, a rich culture, and the rich cultural exchange between Christians, Muslims, Jews. And this is how many of the names came then to us. Mostly, of course, from navigators. Navigators that were passed on. Okay, so that's where the name comes from. And we have seen it's going to explode and Orion is going to lose its shoulder. Tomorrow, 200, or maybe 200,000 years. We can't say. So 2 years ago, 1.5 years ago, it looked as there would be something very interesting going on because it became dark. It's usually the 7th brightest star, and suddenly it was only the 35th or 40th brightest star. The most likely thing is it basically pushed away a gas cloud. And when the gas cloud got colder, it blocked away loads of light. Or scattered it away. That was one thing. Or that there are a couple of this burning cycle, like the Cepheids, where it gets bigger, smaller, emits more light, emits less light. And there are a couple of these different ones. And that they all coincided. But I would say it was most likely that it basically starts becoming a planetary nebula. So, but what happens then? Well, Betelgeuse is a relatively massive star. Massive star we have seen. They can burn quite for a long while. Oops. So let me share screen first of all. Stupid me, forgot this, and so you had to do my face. So you should have now the screen. Up now, let me get everything nicely adjusted so that I have it a bit easier. Sorry, but I'm getting old and comfortable. So we have seen basically the massive star possibly can burn up to iron. At some point it won't be able to sustain nuclear fusion anymore, even if it's beforehand. And then we have a core of something heavy, a heavy element. If the particle number density is still the same, the density has drastically increased from hydrogen with 1 mass number to iron with 56, 57. Rather nickel at this time. More. So the density is much, the gravitation that the core produces for itself is much, much higher. And then, of course, you still have the stuff that is on the outside. Even if the star is now swollen up, you still have a lot of material that is pressuring towards the center. So we built basically up a non-burning core. What will stabilize this non-burning core? So if you have a star that is sufficient to undergo the silicon burning, we will build up this iron nickel core. The only thing that works towards the outside is again the electron, the degeneration pressure of the electrons. Iron or nickel 56, as the name says, is 56, and even nuclei have a particularity that their angular momentum is usually 0 in the ground state. This means we have an integer number 0, 1, 2, 3 of the angular momentum. These particles are called bosons. This is usually associated with the exchange particle Morse, but sometimes in compound system, atomic nuclear compound of many of these fermionic protons and neutrons that underlie the Pauli principle. For any strange reason, the nucleus is then a boson. They can become a boson-Einstein condensate. Oh, it's one of these very strange things where they can all be found in the same state, but not at the same place, because then the individual fermions would again repulse each other. Okay, so we have this massive gravitational pressure trying to contract the system, and only the electrons keep it going. And then, of course, this works until the Chandrasekhar mass. That becomes energetically favorable for the electron to search itself a proton and seek refuge in the proton. If one does it, immediately all the others do it, and we get a chain reaction. And all this nice iron nickel core, quite a bit of a mass, will basically, what happens is the iron nuclei, when the protons become neutrons, become very neutron-rich, the nuclei fall apart, and all this work we invested to create them, at least the ones in the center of the core, they immediately neutronize. They fall completely apart. Also, the nuclear around the shell around this will fall apart. We get more individual protons, alpha particles, this kind of stuff. Again, a soup, but we get a massive amount of neutrons as well. And this happens in such a short time. What will happen? You have this iron core, which are atoms, or at least ions that repel each other. So suddenly you have a soup that in next to no time the core collapses. And from basically, well, of course, the density is much higher than normal density that we can create. Nevertheless, it's compared to what follows, it's almost low density. And then you have atomic density, and in the atom, if you take a football stadium and put a pinhead on the kickoff point, most of the stadium has a very low density of only a few electrons, and only the almost entire mass, so 99.95%, is concentrated in this pinhead. So basically, you reduce from the stadium back down to the pinhead. The pinhead next to pinhead, and what happens is even the pinhead are squeezed by a factor of 2. So the density that we get in this core. First of all, in the final result, it's twice as dense as normal nuclear matter. In the core collapse, you get, of course, an overshoot. So there it's 4 or 5 times as dense as normal nuclear matter. The stadium collapsed to not only a pinhead, the pinhead is again only a fourth or fifth of its original volume. Oh. Oh. Then you can see there is a lot of more or less vacuum. There's no bigger force than vacuum. So all the outer shells are now falling into, start now to fall into, get accelerated towards the center. The inner shells, when they hit, this is basically a super dense core now, which will also rebound. But this is for its absolute, this is a wall. So it just gets reflected and falls then towards the outside while the stuff is still falling in. Oh, loads of energy is going to be released, all this gravitational energy, which is partially used to break up these nuclei, but still, then all the stuff that falls in, so the gravitational energy of the outer stuff, it's get rebounded, and now you have dense matter floating through dense matter at a given velocity. You get a lot of nuclear reaction, producing energy, and boom. And you get one very special kind of nuclear reaction that produces also loads of energy. Neutron capture again. Neutron capture one still gets this binding energy per nucleon. So binding energy for one nucleon out is 6-7 mega electron volts. If you go to radioactive nuclei, it might be a bit less because they have such a neutral excess. Well, again, the typical time scales. So if you take a 25 solar mass star, something really big, and we have the different burning phases, and 70 million years or 7 million years, 700,000 years for the helium to carbon, carbon to oxygen, a couple of hundred years, oxygen to silicon, half a year, silicon to iron, the last final stage one day. So if this happens, it's not long to go. And then the core collapse, that will be in a fraction of a second. And as I said, what happens is basically the electron stabilizes for a while the system against gravitational contraction until the Chandrasekhar mass. And then we get these electron capture reactions, produce neutrons, and loads and loads and loads of neutrinos. The electrons seek refuge, and then the core collapse basically happens in the split part of a second. From something that is as big as the Earth down to maybe during the initial collapse phase, less than 5 kilometers. Later on, it bounces back to about, is it radius or diameter? That's always what I mix up. The final remnant depends then also on the mass of a star. We come then back later to this. Well, obviously we get this bouncing back, the outer material falls in onto this very neutron-rich core and bounces back. You get basically this pressure wave going to the outside. And we would expect to have no nuclear reactions, heating up everything. Oh, so this core collapse. Now what happens if one looks into simulations? This is quite a nuisance. I remember one of my first scientific conferences. I was a PhD student, and then there was a plenary talk about supernovas. Core collapse supernova, what we are talking now about is type 2 supernovas. Oh, I look forward to see this biggest explosion that were imaginable back then. Entire big star. Wow. Oh, then the guy showed us simulation in 2D and it nicely exploded. And then he showed it us in 3 dimensions. There was no explosion. So it was basically going outwards, making lots of fuss. But then turbulences kicked in. So we have this collapse, the core hardens, it bounces back. We get also this heating of these reactions here, but most of the energy comes basically really from this gravitational bounce back. And then of course you get turbulences. As every time when you have a fast moving type of liquid, you get turbulences. In hydrodynamics, that's called the Reynolds number, a certain velocity to viscosity relation. Or to get turbulence, which costs a lot of energy. And that suddenly the 3-dimensional stuff didn't explode. It was not only me, there were a lot of people disappointed. This was basically almost that. Oh, foul tomatoes flying in. Oh, it was a bit. What can the poor guy do? That's his simulations. We go from 2 dimensions to 3 dimensions, and these turbulences are so taking so much energy out of the system, it doesn't explode anymore. So you would basically get after 90 seconds of milliseconds after the core collapse, stuff comes out, but in this highly dense viscous medium, you get all these turbulences, and they cost you basically the energy you have. You can nicely watch now 2 dimensions, where you get basically this inbound of this. You will see on the very bottom left how the core collapses, how the stuff falls in, how it goes out again, and then these turbulences, and they eat up. Oh, we have a problem. We know these stars explode. We have seen it happened. The gas clouds are there with a remnant in them. The remnant is now depending on the mass of the star. Whether we get a neutron star or whether we get a black hole. There is again, some people say 15 solar masses, some say 30 solar masses is the difference. Sometimes it can be, of course, a lesser. It's just a question when the material is not accelerated fast enough, it might fall back in. And then the mass exceeds again a certain limit, which I think is the Oppenheimer-Volkoff limit for neutron star to be stable against gravity. What can a system of neutron now stabilize against gravitational collapse? Exactly, neutrons are fermions, Pauli principle. They are like the electrons, they are loners. They would like to be all in their own little quantum state. Therefore, they develop a degeneration pressure that is working against, which works for a certain amount, and then we can even compress them so dense that they will start forming a black hole. So we need, if you take now a look at this film, so best stop now this video, open, click on the lecture slides on this connection. I can't do it here because then YouTube complains again with copyright, and this here is educational stuff. I don't have any commercial interest, and if I would ever earn a penny with this type of videos, I promise that I would donate a good fraction, and the other parts I would invest in toys for my boys or beer for myself. So, well, at the moment I would have a charitable organization that needs every penny. The football club that I support, which is very likely to go. At the moment it looks as we are going down again. Okay. So we have now these problems that our stuff doesn't really work out. But now it turns out that most of the energy from this collapse is not given away in light, it's not given away in kinetic energy. It's given away in kinetic energy, but a large fraction goes towards these little neutrinos that are produced in the electron capture reaction. And during the inbound, this matter is so dense that even with this low probability to interact with matter, the neutrinos are still trapped in this contracting core and only released when it's bounced back at a certain density that the neutrinos come out. And now these neutrinos, well, they can induce, well, the probability that they do so is low, but there are so many that even this low probability is enough that the few reactions that they induce, they are enough to heat everything up. Then, boom, the star explodes. The nova is going on. And a lot of these neutrons, from at least on the outer shells of this core, are also going into space. It's the nuclei that come in. See now a lot of neutrons coming towards them. Because there are so many. The newly formed nucleus doesn't have any time to think, oh, I'm radioactive, I would like to beta decay to become have an equal proton-neutron ratio and become stable. Before it even thinks, oh, I am, there's another neutron. Then new nucleus, before he can think, oh, I am, there's another neutron. So we get now loads of neutron captures. Or the capture for neutron, the probability for neutron capture is much higher than for beta decay. What means beta decay where a neutron becomes a proton, we would go closer to stability again. Oh, and it's this neutrino, this is then called a neutrino driven wind, or this neutrino heating that is then happening, which is sufficient to there's suddenly so many neutrinos at this reaction. You produce so much energy at once. Whoosh. Oh, then the shockwave is sufficient. For a long time I had problems for years and years and years with this idea of the neutrino-driven wind. But because I thought this is a gradual process, or from the core to the outside, this neutronization happens, and therefore the production of neutrons. And never that this core is becoming so dense that even neutrinos can be trapped, what means they're all produced at different time during this collapsation, but they're all trapped, and only when you rebound and under a certain limit, the neutrons can at once go. Oh. Okay, this would lead to what is called the rapid neutron capture process. It means we get now very fast neutron capture, go along here, away from the value of stability, mostly down here. This 28 is not exact, because most of these nuclei are split up again, and we rather start below here. So we have a 20, 28 already matching neutron numbers, and then we had to learn with nuclear physicists that our magic numbers are not sacrosanct. For very neutron-rich nuclei, for example, we have learned that 20 is not a good magic number, it's 16. the subshells are migrating around. And recently we had to learn that even our nuclei in excited states, our shell structure is not a skeleton, it's wobbly. It changes even if you just excite one or two nucleons to another level, and the other proton, neutron, or if it's protons, mostly the neutron migrate around, because they migrate around the proton. It's called type 2 shell evolution. Yet, of course, then every time this beam hits a neutron, where they do not want to capture neutrons. These are the nuclei, because the capture reaction is so unlikely, even if there are many neutrons coming along, the nucleus has a certain time before it picks one. And this time he has a good chance to decay radioactively. It means he would go one step up here, needs another neutron to pick up magic, and the same game. What means here for a while we pile up. Once it made it over, whoosh, it goes to the next magic number. Where again we get this pile up, but then whoosh. Well, so this type 2 supernova was one of the two. For a long while it was the exclusive R process side. Nowadays, of course, one has to admit neutron stars still contain about 5% protons. So we can still make there a lot of neutron-rich nuclei when they merge. And since they are not head-on collisions that then come to a standstill, that they are usually going sidewise. I mean, some stuff is overshooting at the sides. There's still a good chance that stuff is still released into space when they merge. And when the neutron star merger happened or was observed, and the herd trampled in the direction everything is neutron star merger. By now, I would say the pendulums start swinging towards the middle. That is either or, so it's and or it's rather an and scenario. That both scenarios contribute. Okay, but you're going to learn that in order to have a neutron star, you need to have a supernova of a massive star exceeding at least 3 solar masses, very likely 8 solar masses, and below 15 to 13 solar masses, depending again on the model. So, okay, where do we know really what is going on, the dynamics? And for a long while, well, all we had, mostly what we had, either we have seen a supernova going off somewhere, we were often missing then the satellites that could trigger it, or what could trigger it is of course the observation of neutrinos. Best their directional observation. We have loads of them coming, or at least a couple of them within a few seconds or a few short time, coming from the same direction. You know there must have something happened. So for a long while we were often just far too late for the dynamics of the real explosion. And here now, a couple of years ago, 2016, just by chance, this lad here on the left side, Vito Musso, who is during the day earning his living by being a locksmith, and his nighttime passion, well, he's Argentinian, so I would say usually I would have assumed it's football, but his nighttime passion is astronomy. He built he got his own telescope. It looks quite professional to me. I'm happy if I can use the binoculars without injuring myself. So he got this new telescope, and then he bought himself a new camera. And to test the camera, he went on this galaxy here called NGC 613, which is about 60 million light years away. But then he did shots with a minute or so, or 15-20 minutes exposure times in a series. And what he observed is basically 4:43, well, must be 5:37, and then obviously in 3 minutes, 2-3 minutes interval. Sorry. We see here this dot appearing, which became brighter and brighter and brighter and brighter. He was very quick, so basically a couple of minutes after he realized it, he immediately called colleagues nearby from observatorium nearby. Or colleagues, don't think that these are locksmiths, so he is amateur called the professionals, and the professionals then, okay, we have a look, and it turned out to be a Type 2 supernova. And thanks to his photographs, we have now the light curve at the early stages of a supernova. This would be then here, basically these points, thanks to him, taken from his photographs. So, and then, well, of course, because it was the earliest light curve we ever had, for an off-going supernova, it's a perfect test case for models. The professionals then, of course, wrote a publication, Nature, which is a very high-profile journal. I'm a bit, yeah, let's say, of course, if I could, I would publish all my research there. But unfortunately, it's not interesting. Yet, what I quite liked is the gravitational wave guys. They could easily have published it there. It's probably the one with the highest impact factor. But they choose a web. Nature is by the Springer, which is a commercial print house. They earn money with that stuff. They went to of the American Physical Society, which is basically rather charity. There to the journal. Was nice of them because with all the citations and the impact factor of these physical review letters where they have published went drastically up. While usually Nature, if you buy it, there might be 1 or 2. I think, by the way, don't buy it. We have a library and they should have it. There are usually 1 or 2 articles about entire physics per week. So it's usually a once in a lifetime experience to publish there. And Vito Musso did so. Very remarkable. If you want, yeah. So this is then the article, and you find DOI. If you go online and give this DOI, it will bring you to the article. There you can get directly which journal number, etc., etc. Okay, but back, he obviously got us now these nice points for the light curve. Or later on, when the professionals and so on, here's the rest frame days after core collapse, 10 to the -1. So obviously here's the core collapse happened somewhere. Then, or first there comes no light out, right? It's all trapped by this incoming stuff. Only when it expands and becomes less opaque, the stuff or the light can propagate out. So we get the light a bit delayed. Well, and then you see basically the professionals kick in, and then the follow-up observations. Cooling, of course, shock, and then radioactive heating. That means now all this radioactive, this very neutron-rich nuclei that we have produced start to decay. And when they decay, they produce, of course, loads of energy, which then heats up the environment. For example, in a nuclear reactor, when you switch it off, it still produces about 10% of its power. You need to wait a while till this radioactive decays go away before it cools down. People in Fukushima have experienced this. So there's always a danger. Okay, and now if you want to see what's really going on, who's interested in more details in this R process stuff, there the heavy elements are present. Here's a nice simulation by colleagues from this China CEE, or this Joint Institute for Nuclear Astrophysics. I think Arnie Abrahamian is there strongly involved, and of course Schatz and so Notre Dame University, and as well as Michigan State University. They show you nicely, basically, over as a function of the first couple of seconds. Or you get this burst out when the neutron flux is massive. You get the waiting points, this accumulation at the matching numbers. And then if one's broken through, the wall is breached. You get again a very fast neutron capture rate, next one, and then you might make it even out of here. And at some point the neutron flux becomes less or dies away. And what happens is that all these nuclei that you produce, these radioactive ones, decay back towards the stability. What happens is, of course, here at this matching number, because you had enriched it, this was basically, this is when you have a wide passageway, and then you suddenly to make it narrow. You will get there all cramped. And if you would have the ones that are made it through, they quickly can move away, but behind you obviously queue up. Okay, so you enrich there the stuff. And now you stop the neutron flux and you have this stuff reduced, it's radioactive, it decays back. This creates us these peaks, the so-called R process peaks. Also, the existence of uranium thorium tell us there must have been a process that basically goes so fast out here that when it decays, it still leaves us significant amount of uranium, thorium, that is then even years and years after the nova still there, billions of years. Here, what helps is the lifetime. That thorium, I think 220 or 232, has a super long half-life of 14.5 billion. The uranium 238 of 6 billion years or something. Then we can start comparing what do we have in 235, which has 700 million years half-life, and what do we have in 238? Nowadays, it's a ratio of 0.5%. This is 235, and or 0.7%. No, 0.5. 0.7%. It's uranium 235, and the other is 238. There's one place on the planet where this ratio is different. This is in Oglu in Gabon. I think it's Gabon in Western Africa. The Africans were the first ones to operate a controlled nuclear chain reaction in a natural reactor. There they find a bit less of this 235. And this is the stuff that is burned away in the nuclear power plants, and you need the 3% enrichment. You can now calculate back, that was about the case 2.5 billion years ago. Every time it rained, you need something that makes, when one of these nuclei splits up, it produces fast neutrons. And for the next fission to create another fission, it needs to be very slow. So we need to stop it down. And this is usually done by water. Heavy water is then even better, but standard water can occasionally do the job as well. Every time it rained, you had water around. You had one of these 235 uranium fissioning spontaneously, producing 3 fast neutrons. The water made it slow, so if they hit another 235 uranium nucleus, it could split, produce again, and you start. But then, of course, the stuff becomes warm, the water evaporates, it's gone, and nothing makes the neutrons slow again. The chain reactions come stop. Okay, so the Africans were the first one to run a reactor. But for us, the existence of this stuff tells us there must have been this fast process. Oh, so and for us nuclear physicists, it's of course interesting, where are the properties right? Where is this really going on? But I'm pretty sure this depends strongly on the mass of the star. What happens all the mass of the neutron star merger? Whether there is one R process side or R process path, I don't think so. But what is my opinion? There are smarter people whose opinion certainly should count more. Okay, so basically we can now produce in the supernova all this heavy stuff. Oh, lucky us. Because even if it's not so much needed for life, this rare earth stuff, which we know why it's rare earth, because there is no magic neutron number nearby. This is quite technological, very important. So this praseodymium, neodymium, samarium, gadolinium, because these are super strong magnets. So you want to use this in your mobile phones, you want to use this in the wind turbines. So, and where did this really happen? Standard example is Crab Nebula. So again, if we take Orion, the belt, Betelgeuse, Orion itself, Rigel, and then we go basically north up to, well, you see here, if you follow these 3 stars, you come close to Aldebaran. Jupiter is just randomly here. If you follow down here, you come to Sirius, which is a relatively close star. But go north or top. In this region, if you have a good telescope, you can zoom in, you see that these are Crab Nebula. This was this 1054, Nova 1054 AD. Then we have a couple of other Type 2 supernova. Type 2, this is this core collapse supernova. We have to distinguish from this Type 1 nova that just explode because the white dwarf nicks material from its partner, from the partner. Here, what we usually find, if one takes here a look with radio telescopes, one finds in the center an object that emits radio waves periodically. What this is, next week. I got to make a bit of appetite for you for next week. Well, 1987, that was really the Large Magellan Cloud. You remember this satellite galaxy, 170,000 light years away. So basically, perfect for us. Why? Because it's also outside of the Milky Way plane, what means there's not too much crap in the foreground. If it's on the other side of the Milky Way, there might be problems because we have to look through all these stars. So this was basically the first row or second row seed. First row is going to be Betelgeuse. Well, that's how the region looks normally. But then one has basically observed there, 1987, a star that was for a short while outshining the entire galaxy, or the entire dwarf galaxy, or whatever the Magellanian Cloud is then. So, and in this 1 second, the star released as much energy or radiation, energy much more, but as much radiation as in its entire lifetime before. For a couple of million years, it's really a bright one. It's producing energy like hell, and then suddenly we see this a second or a couple of seconds. Oh, yeah, good. Yeah, a second, it shines so much that you can imagine that it can suddenly compete with this billion of other stars around and outshine them. Oh. Okay, so we get these light curves. Can this compare? But we have seen, if we want to look in the center of our sun, what are we doing? We are not looking at the photons, not at the light, these neutrinos. If the neutrinos play really such an immense role, so you remember this, basically this, either the neutron decays or the proton becomes a neutron by capturing this electron. We just turn now the direction of the arrows around and then get the inverse process. Or then we also change basically here the charge. What's coming out is these antineutrinos. Okay, or in this case, a neutrino. So they should come. What is the observation? Well, this is, I think, superconductante. This is the standard rate, 1987. Oh, this was Christmas for them. 10 Christmas at once. So indeed, there was this massive flash of neutrinos. And then you imagine this is 170 million light years. 170,000 light years away, sorry, factor 1,000. And then you have this tiny volume, in spite of this massive tank in the Kamiokande mine. What an opening angle do you have? And then how unlikely is it really to observe one of these neutrinos that come along? What a flux this must have been. Now, the star releases basically this 1 second, the same amount, but the light output is only the 0.15, let it be 0.1, or let it be 0.5%. Loads of kinetic energy of the ejected material. What you have seen previously, this Crab Nebula, is now 6 light years across, 1,000 years later. 6 light years, from nothing to distance between Sun and its neighbors, even exceeding this. Well, but more than 99% is going away via the kinetic energy of these neutrinos. That's why even if this is a small fraction is only converted to additional heat, this is the one stuff that explodes. The star outshines its galaxy with the light, but still this is a small fraction of the energy that is released, which which is taken basically mostly, of course, from the gravity, the gravitational energy that you had. Something iron sphere bigger than the Earth, compress it to maybe 15-20 kilometers. If it's a neutron star, if it's a black hole, even far less. Oh, and then 1987, one would have expected to find a neutron star. It took ages to find this. By the way, these are the later pictures. These are basically the ejector, but they move no away. This is photographed in 86, 99. So this should increase this stuff. And then one can look, of course, with this Hubble, see nicely the pictures. Then we look again with Chandra, where is it really hot? Where are the X-rays coming from? Atka, that is probably infrared again. I would have to look up what this Atka is, sorry. And then we can even look at the dynamics of the ejector. We can now look what particular X-rays are these. So what has been maybe produced beyond iron. Or again, up to iron and beyond iron. Well, the good thing for us, the starting mass is more than 8 solar masses. So let it be more than 3 solar masses. Let's assume this 8 solar mass, so this is nicely between 3 and 15. The average is always a good thing to be based on. Well, it took ages in this 1987 supernova to find the remnant of the neutron star. There should have been a neutron star and took ages. It was a long interplay between experiment and theory, and I think 2 years ago it has then finally been confirmed. At the first one saw there's so much material falling back onto the neutron star that it exceeds a certain mass, and that this Oppenheimer-Volkoff limit, and then it becomes a black hole. So that there is rather black hole left, but now the neutron star has been confirmed. But the good thing is there is a discrepancy of 8 minus 2, with 6 solar masses. Most of the material is ejected into space and forms this nebula. And this is now enriched in the chemical elements. Of course, if it's a generation 1 star, the remnants have then a certain distribution, and then you form from this nebula another star. Stuff goes on again. By the way, the formation of the second generation is now a bit better, because there's with this heavier stuff to get a bit more effective cooling of the original cloud. But honestly, I've never understood this. Yet you have basically already enriched materials. And then you go again, and you enrich with the second generation nova more, and the third generation you enrich more. So you breed more and more of these heavy chemical elements. And this is nowadays, for example, people are hunting for very old stars by looking the chemical elements that you really have. This is also, I don't know if I mentioned this already, astronomers, they have basically 3 chemical elements. This is hydrogen, helium, and the rest is a metal. And then they call the ratio of these heavy elements to hydrogen and helium, they call the metallicity. If the metallicity is high, you know this is second, third generation. If it's low, and some of these stars almost don't have any kind of metallicity. This is the absolute first generation. And the hunting for this is, of course, the astronomers are always hunting for the biggest, smallest, richest, poorest, and and I have to say that what I heard, I'm not exactly sure that Anna Fabled, she's now at MIT. She was 2 years ago. She was in Glasgow, giving a talk, very impressive, because she had not long ago before given a birth. And what can you do when you give a talk? You cannot always just at a conference. Either you cannot travel, or it was in person. She was giving basically the talk with the little boy on her arm. Very impressive. And seemingly she has the oldest star so far. This is called then the Fabled Stone. Okay, but it's quite interesting. Basically, we produce now the seed for the next generation. What is often used for the remnants is also the X-rays that come out, the type of X-rays. If there was a very violent environment, you would expect that the atom that then comes out is stripped of a lot of electrons. And therefore, the X-rays look a bit different than if you have more, basically loads of electrons still attached. Like in a still violent, but not so super violent. Like, for example, the 16 times positively charged iron, which means 16 electrons are taken away, or 24 times. So this is then rather the fingerprint, this type of X-rays that come out, which is a bit slightly different than the ones from these fully stripped ones. As again, atomic process, X-rays usually come when you jump to an inner, or the electron jumps to the very innermost orbitals of a heavy one. Since this is usually occupied like here, you need to kick out one, and then an outer one can jump in. Because you have now this 13.6 evolts ionization energy, and this is multiplied with Z squared. If you have Z of 13.6, that is ultraviolet light, or the hydrogen. X is an X-ray, so if you make it 10, Z squared is 100, you are already in kilo electron volts, which is X-ray energies. Even for an element 10 up. So so X-rays can help us to determine what type of explosion happened here. So this Kepler nova, the Tycho Brahe nova, they were the type 1a according to these fingerprints, while Cas A, or Cassiopeia A, whatever these W49b's, they are rather type 1bc. There is then the different, I think, what type of white dwarf you had, whether you still had a hydrogen envelope or whether you had stripped of all the hydrogen, just the pure oxygen carbon core, or type 2 supernova. The difference here is now type 2 supernova, you usually find a remnant in the corpse of the dead star in the center. So, as we have now seen the fate of a star, so basically now you're basically expert for this kind of stuff, for these figures here. We've seen we have a star-forming nebula, the Eagle Nebula, or Orion Nebula. We form proton stars, and then depends on the mass. Whether we get a mid-sized red dwarf, blue dwarf, white dwarf, what we had this last time. We get the light chemical elements formed and via this planetary nebula occasionally recycled, or via type 1a supernovas recycled into space. And high mass stars, so everything above 8 solar masses. We get the red supergiants and at some point the nova, which nicely recycles a lot. And then depending on the mass of the star when it becomes nova, we get a black hole or neutron star. And here, of course, was this mistake that Kepler star, which is not the Crab Nebula, that, well, I don't want to throw a stone, I'm not without guilt, I also make mistakes. Can happen. Okay. So does this have any consequences for the Earth? Living with the threat that Betelgeuse goes off, becomes nova, and we get massive amounts of light, where certainly a good amount will be very hard X-rays. Or even coming from nuclear reactions, that gamma rays is super hard light. Well, fortunately, we know they are usually absorbed. So if we are here, oops, this is the hard side. This is no different to what I have shown you in the first lecture. So the hard stuff, gamma ray, X-ray, ultraviolet, or visible part, infrared, and so on, radio. And we have basically seen that the hard stuff is absorbed in the atmosphere. Yeah, chaos. Yes, if it's too close, everything beyond 150 light years would be dangerous. Because the light is then so hot, it might sweep away large fractions of our atmosphere. And then suddenly, if the air pressure drops to just half or tenths, or maybe even further, that's it. It would be the end of life. So, not good, not good. And of course, one is coming then later, and all these X and gamma rays are easier to penetrate through the thin atmosphere and might reach the surface. And then anyway, this is mid to long term, it's cancer for a higher organism with multiple cells. So not good. Good thing is for Betelgeuse we are far. It's enough away. Yeah, basically first row, but the first row is safe. Okay, so most of them are basically absorbed and in the upper layers of the atmosphere. The atmosphere is relatively safe. Yet, upper layer of atmosphere, we have a bit of oxygen, but also a lot of nitrogen. Molecular. Now, if you have X-rays, everything, UV light already cracks molecules. So the bond between the atoms that bonds them together to become a molecule, there is enough energy to overcome this. And then you have free electrons, free atoms, often an ion, which might, in terms of oxygen, attach to another O2 molecule and forms O3, ozone, which is good to have in the very upper layers of the atmosphere because it absorbs UV light. It's not so good to have it on near the surface because there usually you have an ionized or an ion molecule which is very, very keen to react chemically. And if you get it in your lung, it's not good for the lung. But what we get now up there is a lot of N2 and O2 molecules crack and form nitrogen oxides. When you create in the upper layer of the atmosphere, then might sink down with a given time. And then it might be in the clouds and brings down to us. Yeah. rain. We got now quite some experience. Today is a sunny day, but I'm fed up with all these storms. Well, and if you do so in the polar region, and for any strange reason, the polar region likes to accumulate the stuff that has been produced in the upper layer of the atmosphere. It's trapped in the ice. And if you have 1 or 2 or 3 years following the nova, where you have this enhanced nitrogen oxide, you should see it in the ice cores. Yeah, basically, ice cores, basically. Every year, when you have permanent ice or snow, every year you got a bit of snow on top. And then if it's long enough, you will press it because the weight on the top layers, on the upper layers is so high. You press that stuff. Then you drill in, and you basically, when you take the core out, you see nicely this layers. And that looks like the annual rings of a tree. And now you can look back, and then you see here's the depth in meters of such an ice core, and then the associated age, depending of course on models, whatever. And then you see an unknown event, the Crab Nebula, another nova that possibly happened 2006, that not even the Chinese tell us about. Here the Crab Nebula, you remember the Chinese telling it? Oh yeah, big star for months. And only this Flaming monk in Europe writing down there was something going on. And who believes a Flaming monk? Somebody who drinks beer with more than 10%. One usually would assume it's from this Trappist. These Flaming monks, they were called Trappists, and they make this Trappist beer. And maybe you have heard of this one with almost 30%, this delirium tremens. This is like schnapps. You consume it too much, you probably see you see all kind of stars and flying pink elephants. Okay, so what I want to show you here is that we really can go through. And then, as in 1604, deposit 1605, as in 1532, deposit 1573. So we really see this in the ice core. And it's not only this, we also see other dirt from volcanic eruption. But now you have seen today how the death of stars produces us basically the stuff, the other chemical elements. Of course, next week we're going to talk again about the corpses of stars, what means neutron stars, of massive stars, neutron stars, and black holes. And then you're gonna see a modified version, and this is the emerging neutron stars instead of just exploding massive stars up to here, exploding one. Then for any strange reason, dying low mass stars now, they cannot produce up to here. But there is something mixed in this, what you find nowadays on Wikipedia, so Big Bang, cosmic ray fission, or yeah. But again, I don't want to blame the colleague, he did a nice work and it can happen. But now you have heard about all these violent events. That if it happens too close nearby, well, and one has now to think that, remember that stars always born in this nearby region and then they start migrating away. This means even after 50 million years, You a star did migrate so much away from your siblings. The bigger siblings, they go off. Fortunately, in this time, you don't have formed life. But later on, if you remain in a region where there is constantly big boys are created and explode, you don't want to have this. So where you want to be is basically a bit in the outskirts, away from the other ones, in order to breed life as a star system. So if you are here in the bar of our Part spiral Milky Way galaxy, there's too much gas, too much stuff is going on, too much stars are created. Then the galaxy rotates. 90% of the stuff is going, I think, clockwise, and 10% is going counterclockwise. Gaia. Remember the stuff that maps our part of the universe. Oh, and it turns out when it rotates, of course, you get accumulation of dust in the spiral arms. This means there you have at the start, at the front, you have usually centers of star creation, and this means occasionally also big ones. And then you don't want to be there. You don't want to be too close. So it's quite good if you're between a couple of stuff of arms, and you don't want to have too many neighbors, because then the risk that one of them becomes nova is too high. You don't want to have it too close. So, I'm now tempted to say thank God, but we are quite lucky. Oh, there is a plan, who knows? But we also learned there is a galactic habitable zone. So if you live too close to the center, where you have loads of gas, stars come, stars go. And loads of gas means you can easily create big ones. Big ones come, go, the rock stars. They're violent. Of course, what happens? You get quite enrichment in heavier chemical elements. Because every star will breed heavy chemical elements from the hydrogen it has. But it's too violent. So it's good to be living a bit on the outskirts. And on the other side, if we go out towards the outer parts of our galaxy, not enough stuff there. The stars that you form are rather smaller. They burn and burn and burn and don't give away their stuff. So it's not violent enough. The enrichment in heavy chemical elements is not there. You can't create life if you don't have enough carbon. At least not life that we know it. So there is a concept of galactic habitable zone where you have enough reaction, but not too many. And we just live in one. Otherwise, well, of course, we wouldn't live. And that's enough for today. So you learn basically the life cycle and the death of stars. Next week, we're going to talk about the corpses. We go to the real big boys. Okay, and with this, well, now to stop share the slides. See you then for our weekly tutorial sessions. Bye.